session of the seminar. It's a great pleasure to introduce Mary Wootters. I've known Mary for a few years. We even co-organized the conference a few years back at Harvard. But more importantly, Mary has been a noticeable presence in a broad landscape of coding theory and computer science. And Mary, of course, Mary graduated from University of Michigan some years back with Martin Strauss, who I had known from Bell Labs as a student, colleague in Bell Labs 20-something years back. So we knew each other for many years. And then after a stint in CMU with Venkat Guruswami, Mary moved to become an assistant professor at Stanford, and that's where she is. Mary worked broadly in coding theory, contributing important papers, and one of them was a boon for me and Tsahi, where we picked up this topic of repairing Reed-Solomon codes, and we were able to ride on the shoulders of giants and contribute a little something to that topic. And then recently Mary, among other things, worked on random subsets and Ldpc codes and thresholds for them in various contexts, and this is the subject of today's talk. And now, Mary, you can begin.
Thanks, Sasha, so much for the very generous introduction. Yeah, so thanks everyone for coming. Yeah, so I'm going to talk about thresholds for random linear codes, and in particular, the punchline result is that Ldpc codes attain list decoding capacity, and I'll explain what that means in a moment. So let me get started by sharing my little whiteboard thingy here. Let's see. Oh, host disabled participant screen sharing. Can whoever is the host allow me to share?
Yeah, you should be able to share now.
All right, let me try. There we go. Okay, can you all see this?
Yes, very good.
Okay, cool. Yeah, so I haven't written any more than this slide, so I'll be doing a chalk talk from here on, but I figured I'd pre-write the first whiteboard's worth of stuff. Yeah, so the talk, there are sort of two names for the talk. One is the coding theoretic punchline, Ldpc codes achieve list decoding capacity. And then another title might be called Thresholds for Random Linear Codes. And this talk is joint work with Jonathan Mosheiff, Nick Resch, Noga Ron-Zewi, and Shashwat Silas. So here's the general outline for what I'm going to talk about today. So the first thing I'm going to do is ask this question: are Ldpc codes optimally list decodable? And I will explain what all of the words in that mean. Spoiler alert, the answer is yes. So I'll sort of tell you the headline result. And then I'll do a quick overview of the proof. The proof is basically going to consist of two parts, step 1 and step 2, and I'll talk about those in sequence. And then sort of give a high-level overview of this one, and this one's not so hard. I'll actually just do it. And then if I have time, I'll prove this step 1, which actually gives a characterization of what sorts of equivalence classes of sets live in a random linear subspace over a finite field. And so the main takeaway that I hope that folks will take away from this talk, the main sort of new tool that I want to highlight is what will be going on in this part of the talk, which is, again, just sort of a characterization of what sorts of sets are very likely to live in random subspaces of particular dimensions. And then this sort of jargon about Ldpc codes and list decoding capacity and stuff like that will just sort of be a corollary of that. So the main takeaway I want to be this tool, and then I'll show you one way to use it. Actually, yeah, so also please ask questions. I guess the point of doing a chalk talk or iPad talk on Zoom is so we can go slow enough that hopefully you should be able to understand all of the details, except for the details that I explicitly say that you're not supposed to understand. So if things are going by too fast, please stop me and we can slow down. Also, just a quick question for y'all. If I use this pen width about this size, is that cool? Can everyone read this on their screens where they are?
Yes, very much so.
Okay, cool. Yeah, and if at any point my handwriting starts to degrade or get too small or something, let me know and I'll write bigger. Okay, so let me start with sort of the first part of this agenda, are Ldpc codes optimally list decodable? So let's get a new whiteboard here. So, whoops. Sorry, still figuring out this writing system. Yeah, like I was saying before we started the talk, this is the first time I've ever given a chalk talk on Zoom. So please bear with me as I figure out how to do this. Yeah, so the first thing is this question: are Ldpc codes optimally list decodable? Right. And let me first, I guess, define all of the terms that appear here. So the first thing I need to define is Ldpc codes, or at least the sorts of Ldpc codes that I'm talking about. And then I need to define list decodable. Do that next. And last, I need to say what I mean by optimally list decodable. So let's start with this thing A, Ldpc codes. So just quick question from this seminar, like, does anyone in this seminar not know what an error correcting code is? Is that something I need to define, or are people okay with that?
I think we're good.
You're good. Okay, cool. Then I will skip that and just say, what do I mean by Ldpc codes? Maybe just to set notation, I will say what I mean by a code. So throughout this talk, a code C is just a subset of f2 to the n. So throughout this talk, I'm just going to be working with binary codes, but everything that I'm going to say also works fine over codes over larger but constant sized alphabets. But let's just stick with binary to simplify things. And I'm interested in Ldpc codes, which stands for Low Density Parity-Check codes. And these are particular codes of the form C, which are the kernel of some sparse matrix. And there are lots of different ways to define this particular sparse matrix. So I'm going to be interested in Gallagher's ensemble of Ldpc codes. And this just refers to a particular distribution on sparse matrices. The actual distribution is basically not going to matter at all for this talk, so I'm not going to waste time by going into it. But maybe just suffice it to say that this is a particular distribution on sparse matrices. And when you look at a code which is the kernel of such a sparse matrix, then a couple of nice things happen. So one, with high probability, that code has good distance. In particular, it lies on the Gilbert-Varlamov bound. And also, Ldpc codes have sort of nice, efficient algorithms. This is one reason why people care about them. So Ldpc codes sort of appear all over the place in both theory and practice.
Mary, GV
Yes.
we cannot attain with constant column weights, correct? We need to allow those to grow.
To attain exactly, you're right, but to approach the GV bound.
Yes.
Yeah.
Mm-hmm.
Yeah, so GV bound minus epsilon, where then the column weights depend on epsilon in some way. That's right. Yeah, thanks. Yeah, so I'm not going to say any more about exactly what, about the properties of this distribution, because it's actually not going to be too important for this talk. But I can go into more details later if folks are interested. Okay, so those are what Ldpc codes are, in particular Gallagher's ensemble. And then the next thing I needed to define was list decodability. So 1b, list decoding. Okay, so we say that a code C is P, L list decodable. If for all points Z in f2 to the n, so think of this as like a received word that the receiver might see, the number of code words C and C that are within distance P of that center point Z, so here dist refers to Hamming distance, is no more than L. So the picture here looks like this. If this is f2 to the n, and here's my code, it's just sort of a bunch of points in f2 to the n, then a code is P, L list decodable if it's the case that, let me get another color here, if for any point Z. In this space, if I look at the Hamming ball that of radius p times n around Z, then there are at most L code words in C in this ball. So list decoding shows up in a lot of different places in coding theory. It was introduced way back in the 50s or 60s by Elias and Wozencraft. And I guess the communication-y way of thinking about it is that if the error you expect is, sort of, if you imagine that a worst case p fraction of symbols might get corrupted, then this is saying that the number of possibilities for the original message, there's no more than capital L such possibilities for the original message. So if L is smaller, that's better. That sort of reduces uncertainty. List decodable codes are also useful just as a sort of as a combinatorial object. They show up a bunch throughout complexity theory and theoretical computer science. For example, they're really useful in pseudorandomness. They're related to extractors and expanders and stuff like that. So it's sort of a natural question to ask. What code, like first, what is the best trade-offs that we can get for list decoding? Here I mean the trade-offs between the rate of the code, P, and this list size L. And then it's also interesting to ask what codes achieve those optimal trade-offs. So that leads me to that last part of this question that I need to define, which is what do I mean by optimally list decodable? So it's optimal list decoding. So fortunately, it's known what the optimal trade-off here is, at least, well, it's not entirely known, but it's known if all we want is that this capital L thing should be a constant. So if capital L, let's say, is a constant, by which I mean independent of n, I think of n, the block length of the code is growing, then the best trade-off between the rate of the code and the parameter p, which was the sort of the radius of this Hamming ball, is rate equals 1 minus the entropy of p. And so in particular, if you look at rates this minus epsilon, then there exist codes which are PL list decodable, while if you look at rates this plus epsilon, there do not exist such codes in the sense that there's always going to be some Hamming ball that contains an exponential number of code words. So this is sort of like the correct threshold here. And the question that we're interested in is which codes achieve this? And in particular, our question was, so returning to our main question, which hopefully makes sense now, are Ldpc codes, or in particular Gallagher's ensemble of Ldpc codes, optimally list decodable? Right, so that's asking, now we've seen all the pieces, if I take one of these Ldpc codes at random, so a kernel of this sparse random matrix, is it the case that with high probability, if it has rate this minus epsilon, then there are no more than some constant number of points in any Hamming ball of radius p for any p? So that's the question. And the answer that we will see soon is yes. And I should say that, right, so what was sort of known about this before, surprisingly, I think nothing was known about the list decodability of Ldpc codes, sort of whether or not they achieve capacity in this model. And it actually seemed to me to be kind of hard. So I've thought a lot about the list decodability of random linear codes. So just take a completely random subspace and ask, is that optimally list decodable? And it turns out that that's a somewhat tricky question. The answer is also yes, but that's pretty hard. And so I would have thought that it would be much, much harder to establish such a result for Ldpc codes because you have so much less randomness to work with. It's still some random subspace, like a subspace according to some distribution, but now it's like the kernel of this sparse random matrix I would have thought that that would be much more difficult, sort of coming from having thought about this question for random linear codes. However, what we'll see is that actually this question is in a provable sense not harder than the question for random linear codes, in the sense that what we actually prove is sort of a black box reduction. If a nice property holds for a random linear code, that is for a completely random subspace, then it also holds for a LDPC code from Gallagher's ensemble. And that's how we will prove that this answer is yes. So I'll say a little bit more about that next when I talk about the proof outline.
Mary, may I ask
yeah.
a question?
Yeah.
Underlying all this, you are imagining a binary symmetric channel, right?
Oh, great question. No. Right, so let's go back and look at the definition of list decoding. There is nothing random here.
Right.
Right, so no binary symmetric channel. Like if we break down this definition here, this says for all Z, the number of code words that are within this distance of the code is at most L. So you can think of this, if you want, as being an adversarial channel. Bad guy picks Z, and bad guy picks the P fraction of errors.
Right. Well, somewhere you said it's optimal, and you mentioned capacity. So I was wondering if there would be an underlying channel. Was that
right?
Yeah.
Yeah. Sorry. Let me just define some jargon then. Yeah, I forgot to define that.
No, it's fine. It's clear. It's no problem.
Yeah. Yeah. So okay. So I won't write it down, but definition, for some reason, I guess because this looks a lot like capacity on the BSC,
right.
It looks exactly like capacity on the BSC, we say that if a code achieves this, it achieves so-called list decoding capacity.
Sure. Yeah.
So, yeah, just a definition. Sorry about that. Yeah. Yeah. Are there other questions? So I didn't, I guess I defined all these terms somewhat formally, but I didn't restate this question super formally. Are there any questions about like what the result says?
So I have a small question. Sorry, are you going to focus on the exact dependence between L and epsilon, the difference between the 1 minus HFP and the ring?
No, I'm not.
Okay.
Yeah, so that's a really interesting question. It's still open, and yeah, right. And I don't know. Yeah, so basically. Actually, well, maybe once I give the proof outline in just a minute, I'll state an actual more formal theorem that we prove, and then you'll see that I'm not going to prove anything about LDPC codes that is not already known about random linear codes, and I will prove everything that is known about random linear codes is now known for LDPC codes. So anything that we don't know about random linear codes, we still don't know for LDPC codes, and vice versa.
Okay, thanks.
Yeah. So for random linear codes, if you want to back off from this rate by epsilon, then your list size is going to be about 1 over epsilon, and that's going to be, we're going to get that result as well. Yeah. More questions? Cool. Okay, so let me move on then to the second point in my agenda, which is the proof outline. So let me actually state the theorem that we do prove. Which I was just waving my hands about. So theorem, I'll put this in quotes because I'll say what this means in a moment. Any local property that is satisfied with high probability. So with high probability, I mean probability 1 minus little o of 1 by a random linear code. Random linear code. So by random linear code here, I just mean uniformly random subspace. Of f2 to the n. So any local property that is satisfied with high probability by a random linear code of dimension k is also satisfied with high probability by an LDPC code from Gallagher's ensemble of dimension k. And so what do I mean by local property? So I'll just say informally, a local property is defined by the exclusion of small bad sets. So in particular, list decoding, which I just defined, is defined by the exclusion of all L tuples of points that lie in some Hamming ball. But I'm not going to define local property anymore. Specifically for the rest of the talk, I'm just going to focus on list decoding, because just to make things more concrete. But this does apply to anything that you can, any sort of property that you can define by the exclusion of small bad sets with certain symmetry properties. And yeah, so in particular, list decoding is such a local property. Actually, I'm going to say this. Yeah. Okay, so then here's another theorem. This is not a new theorem. So here's a theorem. So many different sources of this theorem, depending on the parameter regime that you're interested in. One source is Guruswami, Hastad, and Kaparti from 2010-ish, I think, or else a result of myself from 2013, or myself and my student Ray Lee from 2018, and there's several other results that could go here. These say that random linear codes are optimally list decodable, or I'll say nearly optimally list decodable, depending on the parameter regime. So then if we take this, this statement and we combine it with this theorem here, that immediately implies that Ldpc codes are also nearly optimally list decodable. So corollary. Okay, so what I'm going to do for the rest of the talk is focus on the proof of this statement then. And let me also say that I'm saying it now in the context of list decoding. It also holds for other things like list recovery, average radius list decoding, average radius list recovery. There's a bunch of different adjectives you can put in front of these things, and they're all local properties that have all been studied for random linear codes, and all of those results then basically carry over for free to Ldpc codes.
Hi, Mary, may I ask another question? This is Prakash again.
Yeah.
So you explained that at this point, everything is purely combinatorial, right? The only randomness comes through the random ensemble. Just to understand, if there were an underlying channel which had some sort of an error, and then you had the probability of a decoding error using list decoding, do these results generalize in some sense where you have extra randomness due to the noise in the channel?
Yeah, that's a really good question. So the question is like, sorry, go ahead.
You mentioned an adversarial channel where somebody flips the bits, and then so you allow a certain number of bits to be flipped, right? That's what you do in effect.
That's right.
If the adversary were to use a randomized strategy, then things would be different, right? Or would it not be?
That's right. Yeah. So if the adversary were to flip, so suppose they weren't that adversarial, if the adversary, quote unquote adversary, were just the binary symmetric channel, then if I have a code of rate 1 minus h of p minus epsilon for the binary symmetric channel, that's below the capacity of the binary symmetric channel. So in fact, Shannon's theorem tells us that with high probability, there will be a unique code word. And so therefore, for random errors in this regime, I won't have a list of L, I'll have list of
Yeah,
Y.
you know, there are channels where when you have an adversary who has some kind of a refined strategy, list decoding can outperform clearly standard codes in the sense of getting you a better rate. So this arbitrarily varying channel is an example.
Mm-hmm.
And I'm wondering what happens in a case like that. You see, then things become different because in those channels, actually, using fixed codes or deterministic codes, there are instances where the capacity is 0, but if you're allowed to randomize over the choice of codes, you can do better, you can get a positive rate. And in those cases, the nature of the channel plays a big role. So if you use list codes, then you can attain a better rate using fixed codes, deterministic codes, compared with standard deterministic codes which don't have this list decoding capability.
Sorry, I'm trying to follow. So you're suggesting that by using a random ensemble of codes rather than using a deterministic code?
Yeah. So for those channels, if in fact a randomized code outperforms the deterministic code in the sense of rate, because it could be that for instance, if you have an adversary who randomizes between two binary symmetric channels, right?
Mm-hmm.
And so that the average crossover probability is half, then using a deterministic code can't do too well. But under certain circumstances, randomized codes do better. But maybe I'm just veering too far from what you do. Maybe we can talk later. I don't want to disturb.
Yeah, maybe we can talk offline. This sounds like pretty far from the.
Yeah. I'm sorry. Yeah.
Yeah, this sounds like pretty far from the model that I'm thinking about. So once again, when I'm thinking about list decoding, it's in this sort of worst case, completely adversarial channel model.
Thanks. Yeah.
But yeah, so getting back to what you said originally, this is a completely combinatorial result.
Yeah.
Just about these subspaces.
Sure.
Actually, on that note, let me just highlight an open question. So the reason we originally started thinking about this was because we wanted an algorithmic result. Like, it would be really cool to have a list decoding algorithm for any code which runs in linear time. So up to this sort of optimal list decoding capacity thing. So that is, you give me as input this center point z, and I return to you in linear time all of the code words within some radius of z. So we thought, well, let's try Ldpc codes, because of course they admit extremely fast algorithms for unique decoding. Okay, first thing we need to do is to show that there's not exponentially many points, because then there's no way I could return them in linear time. And we did that, so now we know that there's constant number of points, but we still have not shown how to actually recover them. So what I'm going to tell you today is just a combinatorial result. It does not come with algorithms, does not come with efficient algorithms, and I think that's a really nice open question. This is maybe the main open question left by this week. Well, are there any other questions before I move on to talk about sort of how we prove this statement? Cool. Okay, so let me, I guess, jump into an outline of this. What are we on? We're on step. Oh, we're already doing step proof outline. Yeah, so first I need to set up some notation. So I said that local properties, which are what I'm considering, are defined by the exclusion of bad sets. So let me just name the set of bad sets that I'm interested in. So let's let curly b be the set of all L tuples x1 up to xl contained in f2 to the n, so that there exists some z such that the distance between z and xi is less than or equal to pn for all I. Right? So this is just my set of a collection of all of the bad sets. If my code contains none of these bad sets, then it is list decodable. So C is PL list decodable if and only if C does not contain any bad set in curly b. That's by definition. You might have noticed that definition of curly B depends on P and on L. Let's just fix P and L for the rest of the talk so that I don't have to carry around that notation on B. So P and L are fixed, and B is just my collection of bad sets that I'm interested in avoiding. And what I want to show to prove this theorem is that if B is unlikely to appear in a random linear code, then B is also unlikely to appear in a random Ldpc code. That would be the main result. So here's the proof outline. So there are two steps. So step one, this is the part that I'm going to mostly focus on for this talk, is a characterization theorem for random linear codes. Right. And so this is why I was going a bit fast over what exactly I mean by Ldpc codes and what exactly is Gallagher's ensembles, because the bulk for the bulk of this talk, I'm going to be talking about random linear codes and not about Ldpc codes at all. So just random subspaces of dimension k. So what do we know about the list decodability of random linear codes? Like I said, there's been a lot of work on it. And basically what we know looks like this. So here, this is the rate of the random linear code on the x-axis. And on the y-axis, I'm going to plot the probability that a random linear code C avoids all of these bad sets in B. That is the probability that it is list decodable, PL list decodable. Right, and what we know, I said this already, is that there's some threshold rate R star. It happens to be equal to 1 minus the binary entropy of P, but assume we don't know that. So that if you were to plot this probability, it's very close to 1 up until that rate, and then it gets close to 0 and then actually 0. So it kind of looks like this threshold type of behavior. And what we show is we give a characterization of the threshold R star. Like I said, we already know what R star is. It's roughly 1 minus the binary entropy of P, but we give a characterization that will actually be useful in doing this analysis for Ldpc codes. And moreover, it holds more generally for any local property, any property that's defined by the exclusion of small bad sets.
A quick question, if I may. This is Sasha. Mary, the width of the transition is not known, right?
That's a good question. For random linear codes in particular. Yeah, so I don't know that it's known for us. What we prove is that if you want to go from 1 minus delta to delta, the width of the transition in our result is something like, I think it's like log n over n. Is what we show. Yeah, I don't know that you can do. I don't know whether or not you can do better. For us, what's going to matter is actually not the width of the transition, but actually this characterization of what is the threshold rate. So that's step one, which I'll spend most of the time talking about. And then step two is, okay, I'm not going to say anything about this now because in order to say it, I need to tell you what step one entails. But step two is use step one to prove the theorem. So I'll get to that after we see what step one is, because then it will make more sense. Okay, but let me start with the next item on the agenda was, maybe I'll just write it up here. Thing three, proving step one. So a characterization of this threshold rate R star. So the question that I'm going to want to try to answer for the next little bit is, it's in red, what is R star? And pretend that we don't already know it, even though we do. Okay, does the question make sense? The goal is clear? All right. So I'm going to try to characterize this threshold R star. So in order to do that, I'm going to need to introduce a little bit of notation. So the first thing that I want to introduce is some notation about types. These are going to be types of bad sets. So what we're going to do is we're going to break curly B. Remember, curly B is the collection of all bad sets, L tuples that live in Hamming balls. These are sets I want to avoid. And I want to understand the probability of avoiding all of these bad sets with a completely random subspace. So I'm going to break B up into types by something that I'll call their row distribution. I'll define these in a moment. So I'm going to think of a bad set B in curly B as a matrix. So I'll draw it like this. Here there are L points, this matrix is n by L. And I think of the columns as being sort of potential code words. So this is, so B is a set of f2 to the n of size L. So I'm just saying, let's think of the elements of B as being the columns of this matrix. And throughout the talk, the rest of the talk, I'm going to abuse notation and refer to B as both the set and also this matrix. Hopefully that's not too confusing. If it gets confusing, let me know and I'll use M sub B or something like that. Okay, so let's think about this matrix. So note that n, the number of rows of this matrix, is much, much bigger than 2 to the L. Because throughout this talk, sorry, I should have said this earlier, I want to think of L as being a constant and n is growing. So in particular, n is going to be a lot bigger than 2 to the L. There are 2 to the L possible rows that could possibly show up because there's 2 to the L binary vectors of length L. And so probably this matrix here is going to contain a bunch of different copies of a bunch of different vectors. So be like a quarter of the ones are this vector, or a third of the ones are that vector, or something like that. So it makes sense to think about the row distribution of this matrix. So let's let tau be the distribution of rows of this matrix. Distribution of rows. So that is, I'll define for x in f2 to the L, define tau of x as the number of times that x appears as a row in my matrix B, divided by n, the total number of rows. Right, so it's just the empirical distribution on the rows. Does that make sense?
Yeah, I think silence probably means violent assent. So
sounds good. Sounds good. Yeah, I guess this is also the difference between the Zoom chalk talk and the in-person chalk talk, is that since everyone's video is off, I don't know if everyone's going or if everyone's like spaced out. But all right, sounds good. Thank you. I will take silence as assent. Yeah, so that's what tau is, and I'm going to just say that B is of type tau. Okay. So I'll say that tau is the type of B. So I'm just characterizing the row distribution. Right. And now one observation, curly B is in fact closed under coordinate permutations. I'll write this up here. Note, curly B is closed under coordinate permutations, because if I have a bunch of sets that are, or a bunch of vectors that are all too close to some z, then if I were to permute all of the coordinates, then that collection of vectors that I get is too close to the corresponding permuted version of z. So what that means is that I can break up B, curly B, into a bunch of types. Think of curly B as a union of types, right? Great. Okay, and so basically what I'm going to do going forward is I want to know, like, what is the threshold at which I'm likely to avoid all bad sets? I'm going to study this sort of type by type and say, what is the threshold at which I'm likely to avoid all bad sets of this type, and all bad sets of that type, and all bad sets of that type? And it turns out that there's polynomially many types, and I'll avoid them with exponentially small probability. And so at the end of the day, we'll take a union bound and it won't really matter. So I'm going to want to study types. Okay, so that's notation number 1. Notation number 2 that I want to introduce in order to say what this characterization is expectation thresholds. Okay, so in order to introduce expectation thresholds, or like to define this, and then we'll also get into what actually is this characterization of this threshold rate R star. Let me just try to figure out what this threshold rate R star is, right? I want to know what is the rate below which I'm extremely likely to avoid any bad sets. So let's just like do out an example, or like do a thought experiment. So the first thing we might try when we're doing this is, well, let's just try Markov's inequality and see how well that does. So first try to get a handle on R star is Markov's inequality. Okay. So in particular, if we can show, maybe I'll just say this rather than writing this. If we can show that the expected number of bad sets contained in my random subspace is teeny tiny, then by Markov's inequality, the probability that there exists a bad set in my subspace is also teeny tiny. Right? So let's just work out this first moment calculation and see what happens. Let's see. Okay. Right. So let's do this like I was saying before, like type by type. So fix some, I'll say bad type tau. So this is a particular row distribution, so that if I am looking at some bad set B, some matrix B that follows this row distribution, that's going to violate list decodability. That will give me too many code words that all live in a ball if every single one of those code words is contained in my code. So fix some bad type tau, and let's let D be the dimension of the support of tau. AKA it's the rank of this matrix B. Right? Okay, so then let's just try Markov's inequality and see what happens. What's the probability that my bad set B is contained in a completely random subspace C? So this is a random linear code of rate, of dimension K, let's say. And B is some fixed bad set of type tau. Right? So what is this? All right, so it's going to be 2 to the k divided by 2 to the n, all raised to the d. And that's because this is the probability that a single vector is contained in a random k-dimensional subspace, and all the vectors are linearly independent. So that means the probability that they are all contained in a completely random subspace those are stochastically independent events, so I get to raise everything up to the d, right? Great. So then what's the expected number of B's of type tau in curly C? Okay, well, just by linearity of expectation, this is the number of bad sets of type tau times that probability, which I'll write as 2 to the minus n minus k times d. Is calculation good? Right, yeah, I'm not doing anything fancy here, just linearity of expectation. Right, so if I want to say, when is this expectation really small? Well, let's solve for k in order to make this thing really small. I'll put it sort of up here. Sorry for my bad board work. So if k over n, the rate of the code, is, let's say, equal to 1 minus log of the number of type tau matrices divided by d times n minus some epsilon, then the probability that there exists a type tau set in curly C, so in my random linear code of dimension k, is going to be at most 2 to the minus n times epsilon. And yeah, all I did there was take this formula and solve for k so that that's the case. All right. Okay, so fun exercise. What was the point of this? So let me actually codify this exercise with a definition. Oops. So definition. So let's let our expectation of tau, I'm going to call this the expectation threshold of tau, and this is going to be defined as 1 minus the log of the number of B's of type tau divided by the dimension of tau times n. Here I'm abusing notation slightly. When I say dimension of tau, I mean dimension of the support of tau, aka dimension of any such bad matrix whose row distribution is tau, the rank of that matrix. Right. So this is exactly the expression we just got from Markov's inequality. So this says that if the rate of my code R is greater than this threshold, we expect little omega of 1 sets of type tau in a random linear code of rate R. And if R is less than that, we expect little o of 1 such sets. So that's exactly what that Markov's inequality exercise is telling us. Okay, right. So hopefully everyone's with me so far. Have just done for first moment stuff. Okay, so let's return to this question. Right, we had this question: what is this threshold R star? So here I had the rate k over n of my random linear code, so completely random subspace. Up here I had the probability that C avoids tau. And what we've just shown is that here's this, expectation threshold RE of tau. And we've just shown that the graph looks something like this. So up until this threshold with very high probability, I will avoid everything, every bad set of type tau. And the question is this the right threshold? That sure would make our job easy if the only thing that characterized this threshold was just this first moment thing, this Markov's inequality, right? Is it the case that the graph looks like that, or is it the case that it goes off somewhere else, and that the threshold is somewhere above this? Okay, so spoiler alert, it's not that easy. The threshold might be actually bigger, but it's bigger in a very simple way. So still Markov's inequality, like this first moment characterization turns out to be the almost right. So let me show why it's almost right with an example. Okay, so see an example of why that calculation, just this first moment thing, is almost right. So let's say that L, which is this, remember the size of my bad sets here, is equal to 3. And suppose I'm considering a type tau, where I have tau of the row 1, 0, 0 is equal to tau of 0, 1, 0 is equal to tau of 1, 0, 1 is equal to tau of 0, 1, 1, and these are all equal to a quarter. So that is, in this bad example, the bad matrix that I want to avoid is some row permutation of this matrix where this is L equals 3, this is n, and n over 4 of these rows look like 1, 0, 0. N over 4 of the rows look like 0, 1, 0. N over 4 of the rows look like 1, 0, 1, and n over 4 of the rows look like 0, 1, 1. And I just want to know what's the probability that a random subspace of some particular dimension avoids all such triples of vectors. Right. Okay, so let's do this exercise that we just did. We can compute this expectation threshold of tau. So by definition, it was 1 minus the log of, okay, the number of matrices of this type. Okay, I don't want to figure it out exactly, but it's roughly 4 to the n. After taking logs, that won't matter so much. It's about 4 to the n. So let's just say 4 to the n for now. The reason it's roughly 4 to the n is because there are 4 possible choices of rows I could take, and I need to choose about equal numbers. So let's call that 4 to the n. Divided by the dimension of the matrix, that's 3 times n, and this is about a third, or this is equal to a third. Okay, so if I were to draw this picture again, this says that if I were to go a little bit less than a third, with high probability, I avoid all such things. And the question is that tight? And so I claim it's not tight for this example. We can actually go further and still hope to avoid all of these triples of points. So let's see why. To see why, I'm going to do a little bit of surgery on this example. I'm going to just remove this column. So it's gone. Right, so now I have a new example with L equals 2. And in my new example, let's call it tau prime. Tau prime of 1, 0 is equal to tau prime of 0, 1. Because if you just look at this matrix here, half of the rows are 1, 0, and the other half are 0, 1. Okay, so that's what's left. And we can just redo this exercise again. Maybe I'll stick it up here. RE of tau prime. So same computation. This is 1 minus the log now of 2 to the n, because there's about 2 to the n, more or less, such matrices B, divided by 2 times n, which is equal to a half. A half is notably larger than a third. So that means that, let's put a half there. What that's saying is that basically I can take this line and I can extend it all the way to here. Because this says that if I back off from 1/2 by a little bit, so if I look at rate 1/2 minus epsilon, then I'm very, very likely to avoid all bad sets of type tau prime, that is all bad sets that look like some row permutation of this. But of course, if I avoid all bad sets that look like some row permutation of this, then I avoid all triples of the thing I had originally, because if I avoid the pair, then I must avoid the triple. Therefore, I can actually extend the probability that I avoid my original bad type tau all the way up to a half. So bigger than a third. Does this example make sense? Okay, so I claim that, and now this is getting into this characterization, I claim that actually this is the only thing that can be going on. This example is the only reason, in some way that I'll make formal in a moment, that the first moment Markov's inequality is not the right answer. Let me say one more definition. So definition, or maybe I'll say informally first. In that previous example, tau prime is, I'm going to call it an implied type. Of tau. So more generally, here's a definition. So let A in F2 L by little l, so it's some matrix with capital L rows and little l columns, be any full rank matrix with, let's say 1 less than or equal to little l less than or equal to big L. So it's tall and skinny. And say that tau is the row distribution of some matrix B, which let's write like this. Okay. We'll go over here. So then the type tau prime given by the row distribution of what happens when I multiply B by this matrix A. I call that row distribution. So this is a distribution over F2 to the little l, so a distribution over shorter vectors. I'll say that this is an implied type of tau. So that earlier example that we saw when we got from tau to tau prime just by dropping a column was a special case when A was a coordinate projection matrix. But more generally, I'll say whenever you can get from tau to tau prime by doing some linear projection, then I'll call that thing an implied type. Definition makes sense? Cool. So going back to this example, you'll see that this logic that I did here, where I looked at this implied type I got by dropping a column, that same logic would have worked if I had taken a linear projection as well. Because if I avoid, because I'm looking at a linear code, a random linear subspace, if I avoid any linear projection of the original set, I also am going to avoid the entire set itself. Okay, so so that sort of gives us a reason why looking at these implied types, like if I, sorry, let me say this precisely. Whenever I can do this Markov's inequality trick for an implied type and it gets me some threshold, the true threshold is always going to be no less than that. And it turns out that the true threshold is actually also going to be no larger than that. So let me state that theorem. So here's a theorem. This is the characterization of the threshold for a fixed type tau.
Mary, can I ask a question?
Yeah, please do.
So before you state the theorem, I didn't understand. So given a type, how do you know that it's bad? Like you completely ignore the fact that it needs to be contained in a ball of radius p times n.
I see. So you're saying, so I'm defining a bad type to just be a type that has that property. It's just a definition. So
a type is a matrix, yes, with L columns.
That's right.
And
a type is technically the row distribution of such a matrix.
Okay, yeah, but it's kind of like the same. So, yeah. and then I care only about bad types, namely matrices that their columns are contained in a small Hamming ball. So, but it's all this calculation, it completely ignored the fact like it didn't differentiate between bad types and good types, or bad matrices or good matrices, or matrices that are not bad. I mean that they are not contained in a small Hamming ball. Yeah,
that's exactly right. And this theorem that I'm going to say also does not distinguish between those things. So the theorem that I'm going to say is, let's ignore for now bad versus not bad. I'm just going to characterize when a particular type is contained in a random linear code. And then later, for our application, we will restrict our attention to the bad types.
Oh, I see. And then the distance will come into the picture. Like okay, thanks.
Yeah.
Mary had a related question. So if I think of it, the type is a distribution on of super symbols of size L. So it's a distribution on sequences of length L, right? So there become zeros for a given. Now, if you have a bad matrix B, so if you think of it as a distribution, probability distribution, empirical distribution, then what does a bad type look like? So if you give me a bad B, what structural property does the corresponding bad type have?
I see. You mean you want something more interesting than the tautological definition?
I'm wondering. That's right. Yeah. So there must be some structure in terms of the underlying empirical distribution. What is that? I was trying to figure it out in terms of things that I know. So if you have a sequence of length n, and then you can define the notion of a standard type. So you just look at the empirical distribution of occurrence of the symbols. And then you can define a higher order type where you look at blocks of length L, let's say in a long sequence of length n. And then the dropping off of the columns that you had, you can just go from an L-dimensional distribution, in other words, on symbols of length L, to symbols of length L minus 1 by dropping off the last symbols in each L-length block. So that would be the analog in a simpler setting where I have a line rather than a matrix. Then if you have a bad B, which has certain attributes, in other words, the subblocks themselves must have some distance properties. Does it manifest itself in the kind of distribution you get? It could be useful to leverage it if you know what it is.
Yeah, that's a good question. So for list decoding, okay, so one version is for something called average radius list decoding, where instead of caring about the number of points in a ball, I only care about the average. Like I say that something is list decodable if there's no L points that are on average too close to some center. In that case, that's pretty easily characterized by saying that I guess you're looking at this bad type. You want some structural property of this bad type, like as a distribution that says that it's basically like, the expected amount of agreement or something.
Yes.
That you have.
Mm.
If you want it for general list decoding, or I guess list recovery or some of these other things, I don't think there's such a clean way to characterize it. And it's possible that if you could, that maybe you could get tighter bounds on list sizes for those problems, which is a question that's still open.
Okay, all right. Thank you.
But yeah, I think it's an interesting question. For some things like average radius list decoding, there's a quite natural characterization. For other things, I'm not quite sure.
Okay.
Yeah. Cool. Any other questions at this point before I state this theorem? Cool. Okay, so right, so this theorem is going to be a characterization of what this threshold is for a particular type tau. And yeah, like someone was asking earlier, I don't care whether tau is good or bad. This holds for any type tau. I'm going to call this R star of tau. This is going to be like the threshold for tau. This is going to be, okay, so the first thing we might have tried, like that first Markov's inequality thing was like, is this just the expectation threshold? Is it just the thing we get from Markov's? We saw that wasn't true by our example. So the next thing we might hope is that we can sort of do that trick that I did before in the best possible way. Right, so let's, instead of looking at the expectation threshold of tau, let's look at the expectation threshold of tau prime and take sort of the best tau prime we can. So look at the maximum over all tau primes that are implied by tau. So that is like going back to this example that I did, like, don't just drop that column just because I said so. Look at all the possible ways you could have done this trick and pick the best one. And it turns out that that is actually the right answer. So that is the threshold. So let me finish the theorem then. So let R star tau be equal to that. Then 1, if k, if the rate of the code k over n is less than that threshold minus epsilon, then with probability, say the probability that C contains a set of type tau is less than or equal to 2 to the minus epsilon n. I'm sorry, I'm going to put a less than or equal to twiddle, and that means that I am ignoring maybe you need to replace epsilon with like epsilon or 2 epsilon or something like that, but I'm just going to be a little bit fuzzy about that. But it's essentially exponential in epsilon n. This is complete abusive notation. Is not anything formal. I guess what I should say is 2 to the minus omega epsilon n or something like that, if we assume that L is constant. But I'm just going to write this because it'll make the computations later easier to look at. And then the other way is that if k over n is bigger than that threshold rate plus epsilon, same thing, the probability that C contains a set of type tau is now very high, 1 minus about that, 2 to the minus epsilon n, where same caveat about I'm playing a little fast and loose with the constants in the exponent there. So that's the theorem. Does this make sense? In particular, you should all be hopefully already convinced of this direction because we basically proved it before. That direction is just Markov's inequality. Right, so the hard part is proving this direction, which is actually not even that hard. Cool. Okay, so let me state a corollary of this before I talk about, actually, yeah, let's state that on the next. Ooh. Sorry, let me state that on another slide. So a corollary of this, so that was for each particular type. As someone pointed out earlier, I care about bad sets. So corollary, so R star, this is the threshold for list decoding, so the threshold for all the bad sets. I claim that this is the minimum over all types tau appearing in my bad set, my collection of bad sets B, so all the types tau that do correspond to bad matrices of that threshold R tau star. So that is, to get R tau star, we sort of do that Markov's inequality trick in the best way we possibly can, and to get the actual threshold, we just look at the worst possible type. Yeah, so just to write this out, this is the minimum over all such tau. Using notation, I'll just write tau in curly b. The max of tau prime implied by tau of this threshold. Okay, and why is this true? Let's see, I'm thinking about time. I could prove this formally, but I don't think it's super enlightening. So let me just say the proof is that we can union bound over all types tau in curly b. How many types are there in curly b? Well, just as an extremely rough pass, I can say the number of such types is at most 2 to the 2 to the L, or sorry, n to the 2 to the L. And that's because that's just like the number of, that's just a very rough bound on the number of types total, because I just basically need to choose these matrices B. For each of the n possible rows, I need to choose one of 2 to the L. Wait, no, sorry, other way around. For each of the 2 to the L possible vectors, I need to choose a number between 1 and n, which is how many of those things appear in that matrix B, right? Yeah, so the number of such types is less than or equal to n to the 2 to the L. My previous theorem had error probabilities that are like 2 to the minus epsilon n. So when I multiply this exponentially small thing in n by this polynomially large thing in n, I can just forget off the polynomial, basically. So basically it suffices to consider any individual type, and then to get the worst case, just union bound over all of them, and doesn't really affect anything. So this gives us now what I claimed to tell you before is this actually gives us a characterization of this threshold for list decoding, and actually it works, like I said, for list recovery, average radius list decoding, a bunch of other things that are just defined by the exclusion of bad sets. As long as you can break your collection of bad sets up into types, and as long as the size of each bad set is bounded, this same characterization works, because that's basically the only thing that we used. I haven't told you the proof yet, but that's the only thing we use. Okay, so how am I on time? When should I stop talking?
Well, we have been planning, roughly speaking, for 90 minutes.
Okay, cool. So I might not get time to actually prove this theorem, although I can wave my hands at the end. But what I would like to do is to show how to use this theorem to actually say this thing about Ldpc codes, which is what I opened with. Because so far I've just been talking about completely random subspaces, and what the heck does this have to do with Ldpc codes? So let me do that. That's sort of the next part of the talk. So thing 4, why this characterization is interesting. Characterization says anything about Ldpc codes. And in particular, why it proves that theorem that I said at the beginning, that Ldpc codes basically inherit for free list decoding, list recovery, etc., from random linear codes. So the reason is that it follows from a lemma. So here's a lemma. I'm putting an asterisk next to it because this lemma is false, but it's false in a dealable with way. So fix some B in curly B. So fix some bad set B of dimension D. Then let's consider two quantities. Let's consider the probability that B is contained in my random Ldpc code of dimension K from Gallagher's ensemble. And let's also consider the probability that B is contained in C, whereas before C is just a random dimensional K subspace. So I said before, we worked out what this was. This is minus n minus k times d. Right, that is very easy to figure out. And it turns out, this is not quite so obvious. In fact, it's false, but modulo some asterisks, it turns out to be morally true that this quantity is also about the same. All right, so let's just take this lemma as fact for now. Or just take it as fact for forever, I guess, unless you want to read the paper. And then let me tell you why this is then enough to prove the statement. So I claim that given this lemma, the statement that I made at the beginning just completely falls out of this characterization, very simply. So given that lemma, let me state a theorem, which I will prove in a second. It's called Theorem Two. I think I probably already stated Theorem One. So if curly B is unlikely to appear in a random linear code C of dimension K, then curly B is also unlikely to appear in a random Ldpc code. Dimension K. Okay, so this was the claim that I made at the beginning of the talk. So let's prove this. Proof, assuming that lemma. So say that K over N, the rate of the code, is less than or equal to R star minus epsilon. All right, so this is our hypothesis. So curly B is unlikely to appear in a random linear code therefore the rate is less than this threshold for a random linear code, right? And let's let tau be some bad type, right? So it's corresponds to something in curly B, and it's unlikely to appear in a random linear code. So tau is unlikely to appear in a random linear code. All right. Okay, so by the definition of R star, by our characterization that I gave earlier, there's only one reason that tau is unlikely to appear in a random linear code, and that is that there is some implied type tau prime so that Markov's inequality does the job. So there's some implied type tau prime of tau such that k over n is less than or equal to the expectation threshold of tau prime minus epsilon. Right? Our character, that's what the characterization theorem said, aka tau prime plus Markov's inequality is enough to establish that a random linear code avoids it. All right. But then we have, like, what is the probability that tau is contained in a random Ldpc code of dimension k? Well, for exactly the same reason as before, because Ldpc codes are linear, this is at most the probability that that implied type tau prime is contained in an Ldpc code. By Markov's inequality, this is at most the expected number of let's say tau prime types in an Ldpc code. And just by linearity of expectation and using the lemma, so lemma plus linearity of expectation, this is roughly, I'll put a squiggle, this is the same squiggle that was in the lemma, the number of tau prime types times 2 to the minus dimension tau prime times n minus k. Right? Because the lemma said that what's the probability that any particular tau prime type is contained in an Ldpc code? Well, it's about the same as it was for a random linear code, which is this. And then linearity of expectation, I just multiply by the number. Okay, but the whole point of choosing the expectation threshold here is that when the rate is less than that, this expression is small. That's how we chose the expectation threshold. So this is less than or equal to 2 to the minus n times epsilon.
A quick question about this probability. It is unchanged from random linear codes, even though you are arguing about Ldpc codes. Is that because we simply take random matrices and it doesn't matter so much whether they are low density or not, or is there any other reason?
Yeah, so that was this lemma that I
Yeah, I remember that. So
yeah, so yeah, why is it true? Yeah, so let me say a little bit. Yeah, actually, maybe I'll have like 10 minutes. So I'll talk about that after.
Of course.
Yeah, but okay, but then just to conclude this, so that's the complete proof then, like, all done. So this just basically this characterization, the fact that Markov's inequality is basically the only thing going on, means that all you have to do is prove a lemma of this flavor that says that first moment stuff acts the same for random linear codes as it does for random Ldpc codes. And then because first moment stuff is all that's going on, it carries over. Yeah, so I'll answer Sasha's question next about, maybe I'll give just a quick sketch of this lemma. But are there any, I guess, questions about the statement of this theorem or its proof before I do that? Cool. Okay, yeah, so the main punchline is that I think this characterization is interesting on its own. It's surprising to me that, like, basically it's only a first moment thing going on, but then it's also useful because if you want to prove something about other ensembles of codes, basically all you have to do is prove that the first moment stuff behaves the same. All right, but now let me, I guess I can wave my hands real quick about, to answer that question. Okay, now I'm going off script because I wasn't prepared to talk about this, or I wasn't planning on talking about it, so I apologize if it gets wonky. But yeah, so what's going on here? I want to know what's the probability that B, like a fixed matrix B, is contained in some Ldpc code. So this is the probability that, here's my parity check matrix. So this is like my sparse random matrix. Times that matrix B is equal to 0. Write this as the all 0 matrix there. So let's sort of think about things like row by row, right? So let's just look at one row of this equation. So I look at one row here. Imagine that I had actually captured some of my little cartoon ones in it. And then I get one row out here. So basically this is saying if I take a random bunch of rows of B and add them together, I get 0. And I want to show that the probability that the sum of, let's say, S random rows of B is equal to 0. I want to show that this is not too large. And then these rows are essentially independent in Gallagher's ensemble. They're not actually independent, but they're close enough. So then I can, that'll be enough. So I just want to show that the probability that one row is equal to 0 is not too large, and then I can just power it up. So how do you show this? So it's basically a Fourier analytic argument. Let's see, how do I do this? Yeah, so let's let tau be the row distribution as before.
Mm-hmm.
So then the probability that this thing, this is equal up to some normalizing factor that I will not be able to do on the fly. This is equal to the convolution of tau S times at 0, right?
Yes.
So now let's take the Fourier transform of this over F2. So this is equal to the sum. So here all of these equals should have normalizing constants in front of them, and I'm just giving up on that. So take the Fourier transform, or just write this in as Fourier expansion. It's like this times -1 to the
characters. Mm-hmm.
Yeah, to the character, and here it's just the character at 0, which is conveniently 1. So just kill that. Right, so it's just the sum of the Fourier coefficients of this thing. So Fourier coefficients of the convolution are product of the Fourier coefficients. So again, up to some normalizing factor, this is tau hat of x raised to the s. And so basically all we want to do is we want to show that this thing is small, so it suffices to show that tau hat of x is small for all non-zero x. The 0, 1, you already know what it is. So how do we do that? So we want to show tau hat of x is small. So let's just write out the definition of tau hat of x. Mm-hmm. This is by definition, again, up to some normalizing thing that I'm going to ignore. Just that. But what is this? Let's think about it as like a, oh, sorry, it should be a W there. Right. This is actually the bias of what happens when I multiply my original matrix B by this vector x. Right, so here I think of these these rows here as being W, and tau of W is basically picking up how many of those rows appear in V. And then I'll give a +1 if their inner product is 0 mod 2, and a -1 if their inner product is 1 mod 2.
Mm-hmm.
So this thing has something to do with the bias of this matrix B times X over F2. So in particular, if my matrix B here has good distance, like meaning that its span doesn't have any code words that have too low weight or too high weight, this is going to be small. And now's where the distance of the LDPC codes come in. This is the only place where we actually use that property. That basically this means that I win. This thing is small whenever this matrix B has good distance. But I know that LDPC codes have good distance, so therefore I don't need to worry about any situations where the matrix B doesn't have good distance, because separately they're just not going to appear in an LDPC code. It's
not only the good distance, it's the narrowness, correct? The maximum distance also matters.
That's right, yeah.
Mm-hmm.
So there are a couple ways to get around that. One way is you can just take S to be even, so that the all ones vector is always contained in that LDPC code, yes. and then I don't care. Yes. So that's probably the easiest way, is to be like, well, suppose there are even number of ones per row. You can also do it for odd, but it's a headache.
Mm-hmm.
Yeah, so that's the quick sketch of how you prove that. So just
very good. Mm-hmm.
Yeah. Okay, so I guess it's 2:30 now. So maybe with that, let me quickly conclude. So just sort of wrap up. The end. Yeah, so I guess the main takeaway that I hope you got from this talk is that we have this really nice characterization of what this threshold R star is. And basically it only involves first moment stuff. And one application of it to LDPC codes is that LDPC codes inherit everything that's true of random linear codes, or not everything, but any local property. So I did it for list decoding, but the only thing we needed basically is that the collection curly B of bad sets that we want to avoid contains a bunch of bad sets that are not too big and also closed under coordinate permutation. That's the only thing we needed. So any such property that's defined that way, this conclusion holds for. And so in particular, LDPC codes achieve list decoding capacity. In separate work, we can also use this characterization to prove stuff about random linear codes themselves, but maybe I'll leave that for another time. Yeah, and I guess I didn't actually say anything about the proof of this characterization. So if we go back to the theorem, the main theorem, here, right, so I did prove this direction because it's just Markov's inequality. I didn't prove this direction, but let me just say real quick, it's just the second moment method. So Markov's inequality is not quite enough, but Chebyshev's inequality is. That's the that's the end. So I think really the hard part of this theorem is figuring out the right thing to look at. So looking at these types and looking at these implied types. And once you look at those and you know you're supposed to use the second moment method, you can probably prove this on your own. It's not that involved. Okay, yeah, so with that, yeah, I guess I'll stop there because I've been talking for an hour and a half, and I'll take take any questions, any more questions anyone has.
Very good. Thank you very much for this exciting, interesting talk. Questions, please.
Yeah, I have a question. In the first part of the theorem, the achievability part, you actually use the characterization to prove it. You don't need the formula in terms of P, right?
That's right.
Yeah. Now, in the converse, whose proof you outlined a sketch just now, do you need the formula, or again, it's done in terms of the operational characterization, or in terms of that characterization, sorry?
Yeah, so it's just in terms of the characterization. So yeah, it's a good question. Yeah, so like I said, this theorem here actually holds not just for list decoding, it also holds for any property that satisfies this exclusion of bad sets that are closed under coordinate permutation. In particular, it holds for things that we don't even know the threshold for. Actually, as a corollary, this establishes that all such sets have thresholds as well.
Yeah.
But
So,
we can, oh, sorry, go ahead, please.
I was going to say, one question of interest to me, and I think also Saki asked that, is in terms of P, L, and N, what are the distributions that, what are the bad types what are the types that fall afoul of list decoding? Something at the level of distribution.
Yeah, so in terms of characterizing those exactly, I don't know, in terms of coming up with particular types that run afoul, as you say, of list decoding or list recovery. Actually, in a follow-up work, this is with the same set of authors as this work, so Jonathan Mosheiff, so it's with Jonathan Mosheiff, Nick Resch, Shashwat Silas, myself, and then also Venkat Guruswami and Ray Lee. We used this characterization and came up with basically exactly that. So if you want to prove a lower bound on the list size for list decoding, then you can use this characterization to do it. And how do you do it? You need to come up with a type tau that is bad for list decoding, meaning that tau has, if I look at all the matrices of type tau, they lie too close to some point. And also you need to show that tau has no implied, that basically this trick doesn't work. Like if you look at all the implied types of tau, the expectation threshold that you get is not large. And so we did exactly that in a paper that appeared in Random this last year. And what the distributions are is actually fairly natural. Let's see if I can remember. I think it's you pick a center point, and then the distribution tau is just a p fraction of the coordinates agree a lot with that center, and a p fraction are uniformly random or something like that. So you cook it up exactly to be that, and then you can show that indeed this doesn't have any implied types that are too small. So you can use that to get lower bounds on the list sizes.
Thank you. Very nice talk. Thank you.
Thanks.
Other questions?
Yes, I have a question. One last question before you will release Mary. So can you go to the last slide or last part?
The Fourier stuff?
Yeah, no, the last one when you wrote. This one. So eventually you will calculate the R star. So for me, I just curious how hard it is to. So you say basically R star equals 1 minus HP. How hard it is to calculate the right hand side?
Right. So that's a good question. We don't. So this is the theorem. It doesn't tell you what R star is. I separately know what R star is because I know what it is for random linear codes because we wrote some papers about it. But that's it. Yes, this characterization doesn't actually tell you what the threshold is.
Proving that there is a threshold is often easier than placing the threshold.
Yeah. So this both proves that there is a threshold, and it characterizes it in this way. And it turns out this characterization is useful, but it doesn't go so far as to say, I can tell you exactly what the threshold is. And in particular for list decoding, we don't actually know exactly what the threshold is. So I said it was like 1 minus h of p, but it should be like 1 minus h of p minus 1 over L, I guess, where capital L is the list size. But if I were to say that, then I would know exactly what the optimal list size is, and I don't. It's an open question. So in some sense, we don't actually know even what the right threshold is for list decoding for general codes. I take that back. Everything I just said was nonsense. We do know what it is for random linear codes because of this other paper where we actually prove a sharp bound on the list size. So okay, I take it back. So we can. Let me start again. This theorem does not tell you what the threshold exactly is for random linear codes for list decoding. In particular, go see that other paper, and we work it out. But it's not obvious and it's not easy.
Thanks.
More questions? Well, if not, thanks again, Mary. Very interesting talk indeed. And we shall be closing this session shortly. And I take it we are stopping for this semester, but we will resume the next semester. We shall, I guess, design a program. This has not yet been done, but some planning needs to be done. But the feeling is, and I think the plan is, that this seminar shall continue.
Oh yeah. No question. It shall continue. It shall continue with the same vigor and
the same mode. Also, whiteboard talks.
Yeah, the mode might continue for a while, I'm afraid.
But Mary, it wasn't difficult, was it?
No, it was really fun. Yeah. Yeah, I guess that you're assuming that everybody has some sort of tablet technology, but I guess that's true because we're all teaching online anyway. So.
Yeah, it was forced upon us, you see.
Yeah.
Forced it.
See, this is one of the silver linings of the pandemic. We have people from all over the world.
Yeah, I started to teach from a camera, but then the students protested. Well, not protested, but they expressed preference for the iPad. So I got myself an iPad, and I guess many of us did the same.
Yeah. Thank you very much again.
All right. Yeah, and thanks all for the invitation and for the great questions. Yeah, this is really fun. And yeah, I was hesitant about the whiteboard talk just because it's been so long since I've given one, or like, cause I've never given a virtual one, but
it's good.
yeah, it went really well.
No, the thing is, when we started this, we said we want to proceed at a pace where we can follow most of the things as in a classroom. And also my own personal experiences this semester, the talks that I've heard, I can remember most of it for at least a month, which is a good sign. So.
Yeah, I definitely prefer chalk talks to slide talks when I'm, in person. It was just the technology, but yeah.
Speed is important. It's just the right pace as in a classroom, and not slides going by fast. So, thank you.
All right. Yeah. So yeah, thanks everybody again. And,
all right.
Yeah.
Bye.
Have a good evening your time.
Bye-bye.
Bye.
Bye-bye.